Welcome everyone to the second lecture of Fundamental of Econometrics in week number 14. This is lecture number 26. We are in chapter 6 and we were discussing autocorrelation, and this is part 3 of Econometrics by example by Gujarati regression diagnostic. In this week we were discussing the remedial measure for autocorrelation. We already discussed the first difference. The model, evaluation, and summary and conclusion will be covered in this chapter. We did cover the part of remedial measure. We will continue our discussion from there, but first to link my discussion with previous learning. So we said that once we have autocorrelation being identified, once we have the autocorrelation being tested and verified by the specified test, then we have three options through which we can proceed. First, the autocorrelation, if it is because of the misspecification of the model, we have to remove that misspecification from our model, and then it will solve automatically the problem of autocorrelation. If there is a minor autocorrelation problem, we can live with it, so that's option 3. And then option 2 is a case when there is a pure autocorrelation. So if there is a case of pure autocorrelation, then we have two options which we can do. First, we can transform our original model to a transform model such that it remove the pure autocorrelation from the transform model. Second is the case of Newey-West method that we can apply directly. So we also did discuss that we use transformation mechanism to solve the problem of autocorrelation, but the transformation required the value of rho. However, rho is not always known. If it is not known, then how we can find the value of rho to use it for transformation? So there were 4 ways through which we can do that. That was the first difference transformation, rho based on Durbin-Watson D statistics, and rho estimated from the residual regression, and finally there is a method of Newey-West. So the first difference transformation is a proper mechanism through which we use the rho value being equal to 1, and we use that on the idea that if the autocorrelation is positive and its coefficient value is close to 1, then we can use first difference transformation, in which we use the rho value being equal to 1, and then we apply OLS procedure to this transformation. This transformation is called first difference transformation, and the OLS is called generalized least square method. This method ensures the autocorrelation problem being solved. The second and third are approximation of rho value from Durbin-Watson D statistic test, or from regressing the residual value on its lag value. These two methods were discussed in detail in a previous lecture, so I'm not going to spend more time on it. And also we did discuss the Newey-West method in the previous lecture. So today I will be more focused on the application side. In fact, it's the continuation of the previous lecture, so I will be discussing the application of these methods in solving the problem of autocorrelation. So just to give you the refresher, we were discussing that while discussing the theory, we did 4 tasks in which we estimated a consumption model, being consumption being function of disposable personal income, wealth, and the interest rate, and we used the US data from 1947 to 2000 to estimate this model. We also used the graphical method, the Durbin-Watson D statistics, and BG-LM test to identify the autocorrelation problem in this model. And for these we did the task which we named as 13.1, 13.2, 13.3 and 13.4 respectively. All these tests confirms that we have positive autocorrelation in our model. Then we focused on the remedial measure. So we already discussed that there are 4 ways through which we can fix the problem of autocorrelation. The first one was the first difference transformation that we did it last time. We did it, applied it in Eviews as well, so no need to repeat that whole process again. Today I'm going to talk about the remedial measure using the Durbin-Watson D statistic test, and remedial measure using the error term, and then I'm going to apply the transformation afterward to solve the problem of autocorrelation. So let me start with now the using Durbin-Watson D statistic for approximating the value of rho. Moving toward practical task 14.2. In this, we have to solve the problem of autocorrelation using the Durbin-Watson d-statistics. So going back to that original model in which we were regressing the log of consumption on log of disposable personal income, wealth, and interest rate for the US data. So we already know that this model has a problem of autocorrelation, and now we want to fix that problem. So to fix the problem, we need to transform this model, and for transformation we need the value of rho. Now the value of rho can be obtained from Durbin-Watson d-statistics. So how can we do that? This can be done first running the model in Eviews, the original model, and then getting the Durbin-Watson d-statistic value from this model results. So and then use this equation, rho is equal to 1 over minus d over 2. This is the Durbin-Watson d-statistic value. You can obtain this equation from Durbin-Watson d-statistic equation. We already discussed the theory, so no discussion required here how we can obtain this value. So once you have the value of d statistic, you can plug in that value in this equation, and then you can get the value of the rho parameter. So I would request you to run this model, and since we already have this model, so you don't need to redo it if you have it already displayed. So once you have that, I would now request you to calculate the d-statistic value using the Durbin-Watson using the Durbin-Watson d-statistic value, calculate the value of rho. So we can just plug in 1 minus, we can replace the d with 1.289219 divided by 2, and when we solve it, we get that the rho value is equal to 0.3554. So this is the value of rho. Now this rho value can be used to transform the original model to the transform model, and then apply OLS to that transform model, and that will ensure to solve the problem of autocorrelation. So how we can do that, that I will leave it for a while. For time being, what we have to take from this discussion, from this task, is that rho can be obtained by using the Durbin-Watson d-statistics, and when we do that, the value we got was 0.3554. Going back, the second way of getting the rho value is using the error term. So I can also obtain the rho value from the error terms as well, and then I can use that for transformation as well. So we already had the Durbin-Watson d-statistic value from the first one, and that's equal to 0.335. And now I'm going to use the Durbin-Watson d-statistic value for the, I'm going to use the second method using the error terms to obtain the value of rho. So how can I do that? I go again to a new task. Now it's task 14.3, solving autocorrelation using error terms. This time what we do, we run the model, original model, the consumption function, which we ran a while ago, and then we are going to use the lag value of the error term, and then regress the original error on the lag value to obtain the value of rho parameter. So that's mean first I have to run this consumption model, which we keep on running again and again, and I forecast the error residual value from this original model, and then calculate its lag value ut minus 1, and then I run a new model which will be ut being regressed on ut minus 1, and the coefficient of ut minus 1 will be the value of rho. So I can use the following step. First I run this model in Eviews, then I click on procedure of the result, make the residual series, name it as a residual, then I run the model with residual being dependent variable and residual lag being the independent variable, and I can obtain the coefficient value of rho from here, and then I can use that rho for transforming the original model. So I will save the results from this output, and we then compare it, that what is the value of rho, and then how finally we can use this in in analysis. So let me go back to Eviews now to apply this mechanism in Eviews and how we can obtain the row from there. But for you people, I would say pause the video first, do it yourself, and then once you are able to do it yourself, then compare the results with what I have shown later on in this video. So I am in Eviews window now. So you can see here I have the variable consumption, disposable personal income, interest rate, and wealth. So I'm going to run regress consumption or disposable personal income, wealth, and real interest rate. I will open it as an equation, and since we have to run it in log form, so I will write log of consumption, then constant, then log of disposable personal income, and then log of wealth, and R as it is. We don't have to take log of R, and I press OK. So I have this result of the original model. Now I have to, you can see it from the screen, I have to estimate the forecasted error value from here. So I go to process. So I go to make residual series. Here I make it ordinary and I call it residuals, and I press OK. I will call it residual and I press OK. So this is residual. I have it here, the new variable. So now I create a new variable which I called residual lag. Residual underscore lag 1 is equal to residual minus 1. So this will generate the residual lag value. So once you have the residual and its lag, so you open them as a group, as equation, and then you regress residual on the residual lag value without any constant, and you press OK. So what does it gives you? It gives you the residual being regressed on the residual, or in other word, it is telling you, this regression is telling you if residual 1 lag 1 move by 1 unit, residual t minus 1 f move by 1 unit, the residual move by 0.3246 units. So in other words, it is giving us the correlation coefficient between the successive value of the residual. So that's another way of getting the residual. So let me switch back to the to my presentation. So we were discussing that how we can obtain or find the unknown autocorrelation coefficient rho value using the error term itself, and we saw that when we regress the residual on its lag value, as has been seen here written equation, it gives us the coefficient of this regression gives us the value of rho. This rho could be used to perform the transformation and solve the problem of autocorrelation. So if we compare it, the original model in which we were regressing the consumption on all the variables in its log form, along with the real interest rate without any log, and then the residual being regressed on the residual lag value, and now it's clear from these two models that the rho value is 0.3446. And we can use this now for transforming the model, this model, and then can solve the problem of autocorrelation. So going back to my main slide. So coming back to the main slide, once we have the values of the rho from either using Durbin-Watson D statistic or using the error term, then we can use the transformation to solve the problem of autocorrelation. So how we can use this transformation? Let me demonstrate that. But first, let me show you a few important points that you should keep in mind while doing this transformation. First of all, since P is almost the same for both methods that we have seen, it's close to 0.34 in both cases. So transformation doing for Durbin-Watson D statistic or transformation doing for row value obtained from the residual lag value is same. So we don't need to do it twice. I will be just doing it for one. I'm going it just to do it for one where row is equal to 0.324. However, we can replicate the same method using 0.3554. It doesn't matter we use row one value or another value, the procedure is same. I just want to show you how this procedure works. It's up to you, whichever value you use. At the end of the day, it will solve the problem of autocorrelation. Both the value will solve the problem of autocorrelation. And these two values are not totally different from one another. So for that reason, I will be just using one value out of that. So for that reasons, for that constraint, I'm going to use only one, and I will be I will be doing just using row is equal to 0.324, and I would advise you, if you want to try it, you can try row is equal to 0.3554 at a later stage as a practice to understand this process. So let me continue now to task 14.4. So once we know the row value either from Durbin-Watson D statistics or from the row or from the error term values. So once we know the row value, the next step is the model. We have to fix the transformation mechanism and we have to solve the problem of autocorrelation. So for transformation, if you recall, we know that the transformation equation, you can link it with the previous background which we have studied, that the transformation dependent variable is the lag value being subtracted from the original value but multiply the lag value with the row. Similarly, the constant term was also with a product of constant being multiplied with its constant term, or the lag variables being multiplied to the autocorrelation coefficient and then being subtracted from the original variables. So you can compare it, the format written here for the equation as the one we have studied or derived while discussing the background for transformation. So it's the same format. So now as you can see here, the row values are shown in red form. The row was unknown. So we already obtained that the row from Durbin-Watson process is 0.355 and the row from using the error term lag value is 0.324, and I'm going to use the value of row 0.324. So I will plug in this value in the above equation. This gives me a new equation in which ln of consumption T minus 0.324 into ln of consumption T minus 1 is equal to then the constant minus constant term multiplied by 0.324. Similarly, log of dpi T minus 0.324 into log of dpi T minus 1 and so on for the other variables. The common factor is that you are multiplying the autocorrelation coefficient value with the lag value of the particular variable, and then you are subtracting it from the original variable. And as we already discussed in the background, if you do this mechanism, the error term become autocorrelated free error term. So once I have this equation, now I have to estimate this model. So now if you see in this model, I do not have a single variable at the dependent variable place. Instead, I have a new variable which is constructed by using the log value of consumption in period T and the log value of consumption in period T minus 1 multiplied with 0.324. So I have to construct this variable. Similarly, I have to construct that constant term. Similarly, I have to construct all the three explanatory variable as well, and then only I can estimate this model. So please keep this in mind. So to estimate the above model, we have to obtain all the variable given in this model, and then Eviews steps can be used to obtain this variables and then run this model. Let me show you these steps in next slide. So in practical task 14.4, transformation once the row isn't become known, we have the same model, consumption in period T, log of consumption in period T minus 0.324 multiply into log of consumption T minus 1, and similarly we do that same for constant, for the DPI, for wealth, for the rate of interest. So following variables are need to be created to run this model in Eviews successfully. So first we need to derive the y underscore new, that's a new variable, that's equal to the log of consumption minus 0.324 multiply with log of consumption first leg. Similarly, we can generate a new variable dpi underscore new that is equal to log of dpi minus 0.324 into log of dpi minus 1 or log of dpi first leg. Similarly, w new is log of wealth minus log of first leg multiply with 0.324. Finally, we have R new or the real interest rate new, that's equal to R and then minus 0.324 into R minus 1 or first leg. We also need to have the new constant term. So we first create the constant equal to 1 and then we do constant underscore new, where constant minus 0.324 into constant first leg gives us the constant new. And then we run this model y new being regress on constant new plus beta dpi new plus beta 3 into wealth new plus beta 4 into R new. This is the new model which we have to estimate. So now I will request you that you people pause this video, run this model, save the result for discussion. Okay, so now I will switch to Eviews to show you that how we can do this in Eviews. So this is my Eview file. I have the consumption, disposable personal income, real interest rate and wealth. This is the data which I have to use. So I have to generate the consumption and consumption in period T minus 0.324 into consumption log of consumption in period T minus 1. So for that I go to proceed. Object generate series, then here I write it as y underscore new and that should be equal to ln. So I will write log of consumption, and then should be subtracted from 0.324 into log of consum minus 1. So now what will it do? It will gives me a new variable y new that should be equal to log of consumption minus 0.324 into consumption leg 1 for log of consumption with leg 1. So when I press OK, that gives me a new variable with y new. Similarly, I do the same for disposable personal income as well. So I will write dpi underscore new that should be equal to first I will write log of dpi so that it generates the log of dpi, then minus, and then I take log of dpi for minus 1, and I have to multiply this with 0.324 being multiplied to it. So here I hope I put it correctly, log dpi, press OK. So I got dpi new. Now I got object generate series. This time I do it for so we do the same for wealth as well. So wealth new is equal to log of wealth minus 0.324 into log of wealth but with first leg. So once we do that, we obtain the wealth new as well. Then we have the final one left, that's the R. So new R new should be equal to log, this was without log, so R minus 0.324 into R minus 1. So I generated these all new variables that were required. The only thing which is left is constant. So I will generate series constant should be equal to 1. Then I generate constant new, it should be equal to constant minus 0.324 into constant first leg. Now I open consumption new, y new, which is consumption new, and then I regress it on constant new, disposable personal income new, wealth new, and real interest rate new. I open them all as an equation. I remove the constant because the constant is already added. I press OK, and this gives me a result, a new result. So that's the new model, which is dependent variable is y new. So that's exactly equal to the product, the original variable subtracted 0.324 into the lag value of the original variable, and similarly we constructed the other variable as well. Let's have a discussion on that. So let me switch back to my presentation. So we run this model, y underscore new is equal to constant underscore new plus beta 2 into dpi underscore new plus beta 3 w underscore new plus b4 underscore r underscore new, where all these variable is being created from 1 to 6 formulas. So we have that, and then we go to the output. So this was the output which we obtained. Here this is the transform model using rho is equal to 0.324, and this was the original model when log of consumption was regressed on the log of dpi and w and using r. So you can compare the two models. You can see number of things in it. The coefficients are comparable in both models. If you look at the log of dpi and the log of dpi new, it's almost 0.80, both comparable. Similarly, the w variable coefficients are also comparable. It's not that big difference in the two. The only known comparison is the value of r, which is statistically not significant in the second model, so that make it not considerable. R square value across both models are not comparable because the dependent variables is not same. And then you can see the major differences in the standard error values. These are different. These are not the same, and the reason for that is that the autocorrelation cause the standard error get affected, and because of that t values get affected. And when you correct it for standard error and t statistic, you see the probability values being changing as well. So that's the one thing which you can see, that the transformation fixed the problem of these standard error for the transform model. If we check the BG test for this new results, we can see here with one lag that the problem of autocorrelation has been solved because both the values are greater than 0.5, so we cannot reject H0, and hence we can say that the problem of autocorrelation has been solved here. So moving toward the results of practical task 14.4, we can see here the model y new being regressed on the new variables being generated by the difference of subtracting the product of the lag value and the autocorrelation coefficient of 0.324 from the original variable. This is the original model, the transform model using the rho value 0.324, and this is the BG test results. And as we can see that both the F statistic and the chi-square statistics are statistically not significant, and it's showing that there is no problem of autocorrelation in our transformed model. So having BG LM test being applied to the transform model which we had, let's go back to our original slide. We were discussing the remedial measures for autocorrelation, and we saw that if we know the rho values using the Durbin-Watson D statistics or using the error term, we can apply the transformation mechanism, a similar kind of transformation mechanism that can solve the problem of autocorrelation. So now we move to the third and final remedial measure for autocorrelation, that's HAC, or newly vest procedure or approach through which we can solve the problem of autocorrelation. So this is practical task 14.5, and this method, as I told you in the theory part as well, that this is directly applied to large samples. So under HAC procedure, we apply OLS method directly to the model, and we ensure to get standard error that are consistent or that provide the blue estimator. So how we do that? We run the following. We first formulate the same original model, log of consumption being regressed on DPI, wealth and real interest rate, and then we open all these, for that we open all these variables in group form, and once we have the estimation window open, is you can see here in the figure 1. You can see here you have written log of consumption being regressed on constant, log of DPI, log of wealth, and the real interest rate. So now once you have that, then you click on this tab options on the top of it. So once you click on this option top, you have a different window, and this new window shows you covariance methods. Within these methods you go for HAC or newly vest method. You select this method and then you press OK. So you will get the results. So this is the result of the original model, and this is the result of HAC method through which you obtain directly the autocorrelated corrected standard error. And as you can see here that if you compare the results of the two models, the coefficients are essentially the same. It's no difference. 0.80 for the first variable, 0.201, 0.002, and it's more or less the same. The slight variation that you can see here is in the standard error. That's not the same. There is some minor variation across the two standard errors, and because of that some minor changes in the t-statistic value and the probability value. But by large the results of the two models are comparable. That shows one reason that the autocorrelation problem was not so severe for us. So to conclude this whole discussion, the results across the original model and HAC estimation shows similar kind of output, which suggests that the autocorrelation was not very serious. And if we look into the autocorrelation coefficient value, that was 0.345. that was not very high. If this value would have been very close to 1, +1 or -1, then we would have a very serious problem of autocorrelation. So in this particular case, we could say that we could have lived with this autocorrelation problem and without disturbing anything, because it's not affecting things too much. So let's move back to the original slide. So the remedial measures, to conclude the remedial measures, we saw that we can use the first difference transformation when we know that rho is equal to 1, or when it's the case of positive autocorrelation. And then if we don't know or if we can't use rho is equal to 1, then we have to guess the value of rho. For that we use the Durbin-Watson d-statistic test, or the error terms being regressing on the lag value of error term. In either of these cases we get the rho value, and then this rho values can be used for further transformation of the original model and then solving the problem of autocorrelation. Finally, we saw HAC, that is a direct method of obtaining the standard error being adjusted for the autocorrelation problem. So that concludes the discussion of the remedial measure. There is only one thing left which we can slightly discuss. That's the model evaluation. So model evaluation refers to the model specification. We don't know that the autocorrelation can be, we do know that the autocorrelation can be for a number of reasons, and one of that was incorrect specification of the model, as I told you in the start of it. So we use the model which is displayed here. This was the model with which we started, now we can slightly modify this model by adding one more variable to this model, and that new variable is the dependent variable of the lag value of the dependent variable. So we add the lag value of the dependent variable as an explanatory variable. So we get a new model in which we have a new variable CT-1 as an additional explanatory variable. So we are saying that the consumption in period T is also dependent on the consumption in period T-1. Now this is a new model, or this is the re-specification of the model, and then we can apply we can run this model and we can see if things do improve. So this model is called autoregressive model. Now this is autoregressive model. Why it's called autoregressive model? As I told you already, that when there is a lag value of the dependent variable as an explanatory variable in a regression model, that model is called autoregressive model, or autoregressive model of order 1. So if we run this autoregressive model in Eviews using the same output, I'm not going to demonstrate that because it's a straightforward task, but I'm directly showing you the result of that. You can see here the results on the screen. First, we do not trust the value of Durbin-Watson D statistic here for autocorrelation, although it shows something, but we do not use the Durbin-Watson D value. Why we do not use it? Because we having the lag value of the dependent variable as an explanatory variable, and that's the violation of one of the assumption of Durbin-Watson D statistic. So for that reason, we applied BG-LM test, and you can see here that both are not rejecting H0. So there is no autocorrelation in this model. So the result of BG-LM shows that the value of, you can add one leg or two leg, both shows that there is no autocorrelation here. So we here can say that we can also specify the given model by considering lag value of DPI or other explanatory variable, or both values of the dependent and independent variable. So this was the concluding remarks that that to improve our model specification, we can also check for lag value of the dependent variable or some lag values of the independent variable, or we can use both to check if it can remove the autocorrelation. So it's a kind of like trial and error. However, I'm going to discuss that in next lecture, that what else could be done to fix the problem of misspecification in a particular model. We are going to have some discussion on that. So finally, to summarize and conclude this topic, the last 4 lectures covered topics of autocorrelation. We were concerned that autocorrelation is a problem of time series data, and we discussed that there are a number of reasons such as inertia, model specification, cobweb phenomena being the major one to cause autocorrelation, and we says that we found that due to autocorrelation, OLS estimator are no more blue, their variants are no more trustworthy, and we cannot trust the results. Then we saw some test, graphical method, run test, Durbin-Watson test, and BG-LM test to check for autocorrelation. Then we applied these tests to real data to detect the problem of autocorrelation. Then we saw some remedial measure that we divided into 2 parts. The one case in which we know that this is because of the specification bias, so we have to fix the specification bias to solve the problem of autocorrelation. And if it's the pure autocorrelation, then we have to use the transformation through variety of procedure which we have saw to solve the problem of autocorrelation, or we can directly use the newly West approach to solve the problem of autocorrelation. So with that, we conclude this topic. Thank you very much for watching the video and being patient to it. I hope you like this topic. Please subscribe our channel, and if you have any question, feel free to ask through comments or writing us an email. Thank you very much.